writing Lewis structures. So you're going to write a skeletal structure of the compound. You'll put the element in the middle, those that are more electronegative around the outside. Count the total number of valence electrons present. Draw a single covalent bond between the central atom and each of the surrounding atoms. And then complete the octets for the surrounding atoms. The total number of electrons used must be equal to the total number of valence electrons that we found in step 2. If the central atom has fewer than 8 electrons, you need to try doing double or triple bonds between the surrounding atoms and the central atom. Using lone pairs from the surrounding atoms, you can complete the octet. So, for example, we have carbon, which has 4 valence electrons, and 2 sulfurs, which each have 6 valence electrons. So that's 16 valence electrons. Carbon would go in the middle, and we would put 2 sulfurs on either side. Bond your 2 sulfurs. So far we've used 4 electrons, leaving us with 12 electrons. We're going to satisfy the octet for the sulfurs. So that uses up the rest of the 12. So I have no more electrons to be used. But carbon's octet rule has not been satisfied. So what I can do is I can take one of my, it's not going to let me do it that way, one of my lone pairs from the sulfur and add it to the carbon. Now carbon has 6. It still needs more. So I'll take a lone pair from the other sulfur. And here both sulfurs have achieved the octet, and so has the carbon. So this is the Lewis structure for CS2. Alright, if we try NO2 minus, nitrogen has 5, oxygen has 6 and 6. The negative charge tells me I have an extra electron. So we're going to add one more electron there. So that's 18 valence electrons. So we would put nitrogen in the middle and our 2 oxygens around it, and we would bond. So we've used 4 electrons, leaving me with 14. Satisfy the octet on the oxygens. So that's 12, leaving me with 2. So I can put those 2 on the nitrogen. So my oxygens have complete octets, but my nitrogen does not. So that means one of my oxygens is going to have to lose a lone pair and double bond with the nitrogen. Now I have all of my atoms with the complete octet. Now because there was a charge, we're going to need to put this Lewis diagram in brackets and show that there was a charge on this substance. Looking up here at number 3, hydrogen has 1 valence electron, carbon has 4, oxygen, oxygen, and hydrogen. So again, that's 18. Carbon would go in the middle. I would have 2 oxygens and 2 hydrogens to go around. 1, 2, 3, 4. So I've used 8, leaving me with 10 electrons. 2, 4, 6, 8, 10. Alright, so now I've used up all of my electrons. So something's not right because I have an oxygen with an incomplete set. So what I can do is instead of bonding my hydrogen to the carbon, I could bond it to the oxygen. But now that leaves my carbon without a complete octet. So what I can do is take away a lone pair from the other oxygen and double bond. So now all of my atoms have the complete octet. Remember, hydrogen only needs 2 electrons, so it never has lone pairs. A formal charge is the electrically charged difference between the valence electrons for an isolated atom and the number of electrons assigned to that atom in a Lewis structure. This helps determine the most plausible Lewis structure. All of the atom's non-bonding electrons are assigned to the atom. Bonds are broken between the atom and the other atoms, assigning half the bonded electrons. So if we think about ozone, O3, so that's 18 valence electrons, oxygen, and then 2 oxygens surrounding it. That's 4, leaving me with 14. I've used 12, leaving me with 2. So the center oxygen is not a complete octet, so one of my oxygens have to be double bonded. Okay, I'm going to rewrite this. Instead of being bent, I'll write it as linear, even though the structure is bent. So now let's think about the formal charge on this. Oxygen has 6 valence electrons. And in the molecule, how many electrons are assigned to the atom? So this oxygen here has 2, 4, 6 valence electrons. The bond is going to be split between those two. So this first oxygen has 2, 4, 6, 7 electrons assigned. This oxygen, if we split these double bonds over here, has 2 lone pairs, or 2 from the lone pair, so that's 2, 3, 4, 5. The oxygen on the other end has 2, 4, 5, 6. Well, we're looking for the difference, so if we subtract them, then the formal charge would be -1, +1, and 0. So how do I know if this is the most plausible Lewis structure or not? For molecules, the sum of the charges must add up to the charge of this distributed ion. 0, because molecules are electrically neutral species. So let's go back to that ozone. If I was to add up my formal charges, this molecule would be 0, which matches the charge on the molecule itself. There's no charge there. So this is a plausible Lewis structure. For cations, the sum of the formal charges must equal the positive charge, and for anions, the sum of the formal charges must equal the negative charge. Formal charges just allow a qualitative picture of the charge distribution in the molecule. It is not to be interpreted as actual charges. So let's try that NO2. Nitrogen has 5, oxygens both have 6. We have that negative charge giving us a total of 18. Nitrogen goes in the middle. We have our 2 oxygens bonded around it. I've used 4 electrons so far, leaving me with 14. Satisfy my oxygen. That's used 12, leaving me with 2. Nitrogen doesn't have a complete octet, so one of the oxygen atoms has to be double bonded. So let's write it out linear, even though we know that it is bent in shape. We can think about our bonds being broken in half. So valence electrons, oxygens are 6, nitrogen is 5. Electrons assigned, this first oxygen has 2, 4, 6 from the lone pair plus 1 to make 7. Nitrogen has 2 from the lone pair, 3, 4, 5. And this oxygen over here has 2, 4, 5, 6. So we have 0, 0, and a -1. Notice when we add up the formal charges this time, it actually equals the charge on the anion. If there is more than one acceptable Lewis structure for a given species, no formal charge is preferable, so if everybody is 0. The smaller formal charges are more preferable, and negative formal charges on species that are more electronegative. So in this example, we would want oxygen to have the more negative charge if that was the situation. So if we were to draw the Lewis structure, carbon is 4, hydrogen is 1 apiece, so that's 2, and then oxygen is 6, so that's going to be 12 valence electrons. Carbon in the middle, oxygen, hydrogen, and hydrogen. 2, 4, 6, leaving me with 6. 2, 4, 6. Whoops. So I've run out of electrons, but my carbon is not satisfied, so that means oxygen is going to be double bonded to the carbon. So that's one way of writing the formula. We could have also drawn it in this setup, where the carbon-oxygen is triple bonded. So then we have to think about our formal charges to see which one is the better Lewis structure. Alright, so let's take the first one that we drew. So hydrogen has hydrogen has 1 valence electron. Hydrogen has 1 valence electron, carbon has 4, oxygen has 6. Alright, so how many are assigned? If we break these bonds, hydrogen has 1 electron assigned, 1 electron assigned. Carbon has 1, 2, 3, 4 electrons assigned. And oxygen has 2, 4, 5, 6 electrons assigned. So those formal charges would all be 0, which is what is preferable. Let's look at the other instance to see how the formal charges would change here. Hydrogens are 1 valence electron, carbon is 4, oxygen is 6. If we were to break the bonds and split it between the atoms, hydrogen still has 1 electron assigned to it. Carbon has 1, 2, 3, 4. And oxygen has 2, 3, 4, 5, 6. Leaving them all 0. Okay, I'm sorry, I just realized that oxygen has more than 8 valence electrons around it, so this is not the correct Lewis diagram. So let me change that real quick. So that extra electron would have to be on the carbon like that. Alright, so let's go back here. Carbon has 2 from the valence electron, or lone electron, so that's 2, 3, 4, 5. Oxygen has 2, 3, 4, 5. So that gives the carbon a -1 charge and the formal charge, and the oxygen a +1 formal charge. So this is going to be the better structure because all of our formal charges are 0. Resonance, a resonance structure, one of 2 or more Lewis structures for a single molecule that cannot be represented accurately by only one Lewis structure. The word resonance means the use of 2 or more Lewis structures to represent a particular molecule. So the position of the electrons, not the atoms, can be rearranged in a different resonance structure. So if we look at CO3 - 2, carbon has 4 valence electrons, oxygen has 3, and then we have that -2 charge, meaning we have 2 extra electrons. So that's a total of 24. Carbon would go in the middle, and our 3 oxygens would go around. 2, 4, 6, leaving us with 18. Satisfy your oxygen. 2, 4, 6, 8, 10, 12, 14, 16, 18. So we've used all of our electrons, but carbon is not satisfied. So one of my oxygens has to be double bonded. It doesn't matter which one it is. That's what resonance is. So it could be this oxygen that's double bonded. It could be the oxygen on the top, or it could be the oxygen on the right. that's double bonded. All of these would be the correct Lewis structures. Well, that double bond, because it could be on any of those three, it actually isn't on any of them in one particular time. So sometimes you might see the Lewis structure drawn with a dashed line to represent the summation of the resonance structures. So if we were to take all of these resonance structures and superimpose them, we would have this double bond appear on all three. So instead of having a double bond and two single bonds, what I really have is three bonds and a third. So I have three single bonds and then a third of a double bond, because it could be here, here, or here. So to figure out the bond length, I'm really going to say that this is, instead of a double bond, but a bond and a third, which would be shorter than if they were all single bonds, but longer if it was a true double bond. Benzene organic compounds are very popular with resonance structures. So we have C6H6, which is benzene. That's one that you're just supposed to be able to recognize. Alright, it's a cyclic compound of 6 carbons and 6 hydrogens. So we'd have one hydrogen coming off of each of our carbons, which means there's got to be some double bonds. So it could be double bonded like that, or it could be double bonded like that. So a lot of times what you see with benzene is people draw this compound and then they put a circle in the middle to show that those double bonds could be anywhere in that circle of carbons.